Welcome to reinforcement learning, and we're going to see how to learn acting via policy gradient methods and how to evaluate the actions via temporal difference updates or advantage updates. So far we have seen Q-learning, which is a model-free set of techniques which is based on the value function. And this is a little bit weird because the goal is to find the optimal policy, but Q-learning doesn't have an explicit representation of the policy itself. So if we want to get the policy, we need to take a look at the Q estimates and take the policy with the highest Q estimates. Policy gradient methods, in turn, they work directly with the policy, but they don't have a value representation. So we don't have an explicit way here to judge whether our policy is good or bad. Actor critique algorithms, they are model-free in the sense that we don't need to estimate the transition and the reward models. And they combine actually the policy representation and the value representation. So basically they take the value-based and policy-based approaches together. So to understand how they work, let's take a look at the stochastic gradient policy theorem and add a baseline to it. The stochastic gradient policy theorem states that the gradient of the value function is proportional to the sum over all states of stationary distribution mu. And that is multiplied by the sum over all the actions of a gradient of the policy. So it gives the direction in which basically to improve times the expected rewards Q that are coming from that policy. Now, if we add a baseline to this, what will happen? So if we add a baseline function that is a function of the states only, then it turns out we can do that and put any function there because the sum over all the actions and the gradient of the policy times this baseline can be rewritten by pulling in front the baseline and also applying the gradient in front of this sum of the policies here. And because this is a distribution, it must sum up to 1, and then we have that the baseline times this gradient of 1 is equal to 0, and nothing changes in our stochastic gradient policy theorem. So we can make use of that by specifying a baseline, and to specify that smartly, people have actually used the value function of a policy to put that as a baseline function. The nice thing about this is that we can specify with this an advantage function. And the advantage function is a function of a state action pair, and it is basically the difference between the Q function and the value function of that policy. So if we make a good action, then this difference, the advantage, will be positive, and if we take a bad action, then this difference will be negative. So we can use, thanks to this stochastic gradient policy theorem with the baseline, we can use the gradient update and use this advantage function here directly instead of the Monte Carlo estimate of one trajectory of the sum of discounted rewards. Now this is going to be really helpful because here we only have the information that actually tells us whether we had a good action or a bad action, and then we update our theta estimates only based on this. So this means that we have faster empirical convergence than if we look at the whole level of the Q function that we approximate here. And here we also have then less noise, so smaller variance. So the reinforced algorithm, when we use that baseline, looks as follows. So we can initialize the policy to anything and also the value function to anything. Then we loop forever and we generate episodes. So we get the triples of state, action, reward observations, and then another triple of state, action, reward, and so on. And then we loop for each of the steps in the episode the following. So we calculate the Monte Carlo estimate of our, so the sum of the discounted rewards. And we take this Monte Carlo estimate, not itself, but we subtract our estimate of the value function from it, and that's then called delta. And with this delta, we update our value function. So we have a neural network here where we have the delta inside, and we do here a gradient version of value iteration, basically, to get the updates of the W's. For the policy, we have a different neural network where we also use that delta. And so here we have the gradient of the log of the policy and use this delta instead of the Monte Carlo update itself to update our theta parameters of the policy. Now, this really pays off in terms of convergence. So here you see that we much more quickly converge here. And here you see the learning rates of the two neural networks. Now, instead of using updates by the Monte Carlo sampling to calculate this delta difference, we can also use the temporal difference update and bootstrap. So the advantage here is clear. Instead of doing the whole episode, we can just take one draw, so the reward at the step n, and the discounted value function in the future step, and then calculate the difference of this to the estimate of the value function to get the delta. Also, this helps to reduce the variance and have faster convergence. Now, this gives rise to an algorithm called actor critique algorithm. And here we initialize again the policies to anything and the Q values also to anything. And then we loop forever. And here we sample actually from the policies, and we execute then an action, observe just a reward in the next state, so not the whole trajectory. And from this we use our temporal difference update here to get the delta, and then we do the update to the value function by just using this version of the value iteration, and here update the policy also using this gradient version of the policy iteration. Now, instead of using the temporal difference updates, we can even do better by using an update, not using the value function, but using the Q functions. And in particular, we can estimate the advantage function by taking here this reward in the current step, at the current step, plus the discounted value function, basically. So this is the same thing as here. And then we subtract from this the expected rewards. So this is the sum of all actions times the probability with which we take an action times the reward we get from this. And so we can use this advantage function also to do the policy update. And again, we get a faster convergence here. So this is the so-called advantage actor critique algorithm, A to C, and it works like follows. So here we again initialize the policy to anything, and then we add here this delta, which is now based on the Q functions and our estimate of the Q function, and the advantage function is then this also this advantage function that is now based on the Q function. And we still put the same delta that we obtained here in the update for the Q values. And for the policy update, we put the advantage function. Now, let's take a look at the deterministic gradient policy and consider the case where we have continuous actions that are deterministic. So if we are in a given state, then there's a deterministic mapping to an action. So that's what the policy is. Now, with this, actually, David Silva has shown that there is a special case of the stochastic gradient policy theorem, which is here, which is the deterministic gradient policy theorem. And the difference basically is that here we have the expectation, and we have here this direct mapping from states to action via the policy, and we don't have a distribution. So this is deterministic, and this is probabilistic. And also we need to take the gradient with respect to all the actions, which we don't have to do here. So with these differences, if you want to see the details, check out this paper. We can take a look at the deterministic policy gradient algorithm, and it looks like this. So here, this is pretty similar to what we have seen before, only that we make use here of the deterministic policy gradient theorem, where we can adjust the update of the thetas based on this deterministic policy. Now here are some references, and let's sum up what we have seen. So actor critique algorithms actually combine policy-based and value-based algorithms. And policy gradient methods can actually be improved by using that baseline, which then critiques the actions explicitly. The actor critique algorithms, they use a learned value function as the baseline, and they can be updated via temporal difference updates and also advantage updates. And the deterministic policy gradients can be used for continuous actions that are deterministic and not stochastic, which might be very natural in many applications. Thanks for watching.